Howdy, everybody. So today we're going to do our very first online distance learning lecture, and we're going to be going through this video. I actually just made a video and then had some bloopers, so I'm doing it again, which is pretty fun. And so what we're going to actually do today, whenever you're doing this, is review a bit about percent composition and determining empirical formulas. Now, both of these things are topics that we covered before spring break, and so this is sort of serving as a review to kind of get us thinking about chemistry again and to sort of get us back into the groove of things. So we're going to do a couple examples with percent composition and then a couple examples with empirical formulas, and that'll be kind of how this specific video is going to go. So for percent compositions, what's important is that you're trying to determine the percent of a specific thing. And for us in chemistry, that's most often going to be an element. So to do that, you would take the weight of whatever element is you're trying to solve for, and you would divide that by the total weight of whatever compound it's in. To be in a percentage format, you would multiply one by 100, and then you would have the percent of that element. And so the thing that's a little tricky about percent compositions is that the information that's given to you can be different. But ultimately, you're going to be doing the same process to figure out the percent of that element. So let's do two different examples where the information that's given to you from the jump is different, but you're doing the exact same thing for both questions. So for example 1, a gaseous compound let's say we have a sample of a gaseous compound that weighs approximately 24.81 grams. The compound is composed of carbon, oxygen, and chlorine. So those are the three elements that are inside of the compound, right? And what we find is that it is experimentally determined that there is 3.01 grams of carbon, 4.00 grams of oxygen, and 17.81 grams of chlorine. What is the percent composition? And so what's tricky about this question maybe is that it seems like there's a lot of information. And so what do we do? And what is the information really telling us? The first thing, and probably the most important thing, is that the question tells us we have 24.81 grams of the compound. And then it says that for every 24.81 grams of compound, we have 3.01 grams of carbon, 4 grams of oxygen, and 17.81 grams of chlorine. That is for every 24.8 grams of the entire compound. So this one actually is pretty straightforward because it tells us the weight of each element, and it also told us the total weight of compound that we have. So to do it for carbon, we have 3.01 grams of carbon over the total weight, which is 24.81 grams. We're going to multiply this by 100. So that's 3.01 divided by 24.81. So that ends up being 12.1%. We do the same process for oxygen. We find that we have 4 grams of oxygen for every 24.81 grams of compound times 100 is equal to 16.1%. And so at this stage, to find the percent of chlorine, there are 2 things that you could do. The first thing is that you know that the percentages of all 3 compounds should add up to what? 100. So we have 12.1% plus 16.1% plus the percent of chlorine, right? Which I'm going to represent with an X. That's what we're solving for. And all of this should add up to be 100%. And then you could literally just solve for X. Just do the arithmetic. I don't want to do it that way just so that we can have as much practice as possible. But it tells us that we have 17.81 grams of chlorine. Divide that by the total. Multiply by 100. So we have 17.81 divided by 24.81. Boom. 71.7%. And so that has gotten us to our final answer. And so what we did was we took the weight of each element and we divided it by the total weight. The total weight in this case, the specific example being 24.81. Okay, let's do another example. Example 2. So we have aspirin, which is a common anti-inflammatory drug. Aspirin has a molecular formula of C9H8O4. It has a molecular weight of 180.16 grams per mole. Determine the percent composition of carbon, hydrogen, and oxygen. So still, as we do for percent compositions, you're going to take, and this is going to seem really redundant at this point, right? You'll take the weight of the element, divide it by the total weight, and multiply that ratio by 100. But what I hope you see here is that you're not given the weights of any of the elements, right? We have carbon, hydrogen, and oxygen. So where are those weights? What you have to do here is you have to think that we're dealing with 1 mole of aspirin. And why are we dealing with 1 mole? Why 1 mole? Well, the reason is because how much does 1 mole of aspirin weigh? It weighs 180.16 grams. So if we have 1 mole of aspirin, we know its total weight. If we can figure out what the weight of carbon is in 1 mole of aspirin, then we will have the weight of that element. So that's basically what we're going to do. So for percent carbon, we assume that, we don't assume, we know that for every 1 mole of aspirin, we have 9 moles of carbon. For hydrogen, every 1 mole of aspirin, how many moles of hydrogen do you think we have? That's right, we have 8 moles of hydrogen. And then for oxygen, same deal. We have 4 moles of oxygen. Now, where am I getting these numbers from? These numbers are coming from the subscripts in our molecular formula for aspirin. And if you think about it, we have 1 mole of aspirin, and there are 9 carbons in every molecule. We will have 9 times that many moles of aspirin, right? Because moles are related to Avogadro's number. So really what it's saying is we have 6.02 times 10 to the 23rd molecules of aspirin, and then 9 times that many number of carbon atoms. But 9 times Avogadro's number is just 9 moles. So you really don't have to think mathematically about that. Just look at the subscripts, and that's how many moles of that element you'd have. Now, I hope you see that we can convert these mole values into grams. So 9 moles of carbon, we know that the molecular weight of carbon is 12.01 grams per 1 mole. For hydrogen is 1.008 grams per 1 mole. And for oxygen is 16 grams per 1 mole. Right? And so these are the molecular weights. And so now let's get our handy dandy calculator out and figure out what these numbers are. So we have 9 times 12.01 equals 108.09 grams. We have 8 times 1.008 is 8.064 grams, and then 4 times 16 is 64 grams. So now I hope you see that we are set up to do the exact same thing we did in this problem. We have, undo. We have, we have the weight of carbon. And this is the amount of carbon. Let's do a fun color. This is grams of carbon in 180.16 grams of aspirin. Right? Because we know that 180.16 grams of aspirin is 1 mole. That's its molecular weight. So what we can do is divide these numbers by the total. So let me erase this. We can fit this all in. The total being 180.16 and multiply that by 100. And so what you'll end up getting is we have 60% carbon. You have about 4.47% hydrogen. That doesn't look very good, does it? 60% carbon, 4.47% hydrogen, and you have about 35.5% oxygen, right? So this question was a little bit different because it didn't tell us the amount in grams of carbon, hydrogen, and oxygen that we have. But we had to convert from mole of aspirin to mole of carbon to grams of carbon to end up with our percent composition of carbon, right? But all that came from the molecular formula. Okay, so now we're going to transition into empirical formulas. Empirical formulas are closely related to percent compositions. And so step 1, most often for empirical formulas, step number 1, is to convert grams to moles. When in doubt, convert grams to moles, okay? Step 2 for empirical formulas is divide all mole values by the smallest mole number. And that's pretty much what you're going to do for every empirical formula. Now, the information that you'll be given and how you get to this stage may be different, but essentially, these are the 2 steps that you do. So let us do our first example. We have a compound that is determined we have a compound that is composed of 34.97 grams of iron, and 15.03 grams of oxygen. Determine the empirical formula. Okay, so what do we have to do? Step 1, convert grams to moles. So we have for iron, 34.97 grams. We're going to multiply it by a what? Right? All you keepers of the conversion factors know the conversion factor, which is going to be its molecular weight. So iron, let me pull up my periodic table on my computer here. Iron has a molecular weight of 55.84. So 55.84 grams, 1 mole. So what is that? 34.97 divided by 55.84. Boom. 0.626 moles of iron. Now we got to do the same thing, but for oxygen. So we have 15.03 grams, multiply it by its molecular weight, or divide by its molecular weight, you could say, which will do 16 grams. So 15.03 divided by 16 is 0.939 moles of oxygen. Okay, so we finished step 1. Step 2 is what? Divide all mole values by the smallest mole number. Well, what's the smallest mole number here? I hope you see that it's 0.626. So what we're going to do is divide both of these numbers by 0.626. Whenever you're doing empirical formulas, it's super important that you end up with a number here that is 1. You should always end up with at least one of your numbers being 1. If you don't do that, something has gone wrong. You did math wrong somewhere. So 0.939 divided by 0.626 is a beautiful 1.5. I hope you see that. So 1.5. We can rewrite 1.5 as 3 halves. Now, 1.5 is what I would consider a really pretty fraction. And other really pretty fractions could be 1.25, 1.5, 1.75, and even like 1.33 repeating. So yes, in real life, you could get lots of different fractions. For us, these are going to be the only pretty, quote, pretty fractions that you'll see. And what that means is that normally we would take these numbers here that we just calculated, and we would write the empirical formula for that. So that would be iron and oxygen 1.5, right? We didn't write the 1 for iron because it's understood. But have you ever seen a chemical formula with a subscript that is a fraction? Oh, goodness, I don't think so, right? So what do we have to do? We have to do something. So let's get rid of all this jazz here. Okay. What can I multiply 3 halves by to get it to be a whole number? What's the easiest thing I can do? If I multiply it by 2, I'll end up with 3. But you have to do the top one as well. You have to multiply all of them by the same factor. So now instead of 1 and 1.5, I have 2 and 3, which gives us an empirical formula of Fe2O3. Now, everyone hold your breaths. I'm going to ask, what is the actual name of this compound? Go ahead and pause the video. Do it. Pause the video and try and name this compound, and then unpause it and see if we get the same thing. Pause it. Okay. So we know that the oxygen has a common charge of -2. So the total negative charge, right, would be 3 times -2, which is -6. We have 2 irons, so 2 times the charge on iron minus 6 has to equal 0 because the entire compound is neutral, right? So 2x equals positive 6, x equals positive 3. So what did I just do? I just solved for the charge on iron. And why is that important? Because this would be called iron 3 oxide, right? Remember, elements as anions take on IDE for their final name. Ooh, naming. Okay, so next example. Example 2. We have a gaseous compound that is found to be 27.29% carbon and 72.71% oxygen. Determine the empirical formula. Okay, so if you're given a question like this and you're asked to find the empirical formula and you're given percentages, the first thing you need to do, right, is assume 100 grams of compound. Now, you can assume any weight. It doesn't matter what you assume. You'll get the final answer to be the same. The reason why I assume 100 grams is because that's probably one of the easiest numbers to work with. What this is saying is that 27.29% of the 100 grams is resulting from carbon. And what does that mean? It means that we have 27.29 grams of carbon. So let's see. So for carbon, now we have 27.29 grams of carbon and 72.71 grams of oxygen, right? If you assumed a number different than 100 grams, you would actually have to take 27.29% of that number, and that would be how much carbon you have. Just assume 100 grams, and you can just use those percentages straight up as grams, okay? So now, just like our first step is to convert grams to moles. So let's convert this to moles. So we have 1 mole is 12 grams. We have 1 mole is 16 grams. I know that carbon on some periodic tables 12.01, oxygen is 15.9, right? But we're getting close. So 27.29 divided by 12, we'll do 0.01. It's 2.27 moles of carbon. And then we have 72.71 divided by 16, 4.54 moles of oxygen. So our step 2 is to divide all mole values by the smallest mole number. What's the smallest mole number here? I hope you see that it's 2.27. So I'm going to divide both of these by 2.27. Sorry, my colors aren't exactly super consistent. So here we get a 1. Remember that anytime you do an empirical formula problem, you should always get at least one of these answers to be 1 at the start. Okay? 4.54 divided by 2.27. What do you think it's going to be? Well, it's 2. Right? And so we use these values to write our empirical formula. So we have C1O2. CO2. This is an example of a binary molecular compound, and it has a name of carbon. The 2 would be dioxide. Ooh, nomenclature. Okay, so that concludes our very first video. Now I'm going to try and draw a cute little snowman up here. So I hope that this wasn't too boring, right? We'll talk about how it went for everyone. Oh, look, precious little snowman. And we'll just keep on trying to make this work. So I hope it wasn't too bad, and I hope that a lot of this seemed very familiar to you, and hopefully you'll get to keep this in your notes forever. Thank you. See ya.